Thank you very much for the introduction, and thank you very much to the organizers for the invite. It's really a pleasure to be here and to have the opportunity to talk today. So I'm going to talk about the sharp concavity of the isoperimetric profile. I'm going to discuss some quite recent results, and I would like to take some time to mention some related open questions and conjectures. And most of what I'm going to talk about is based on joint work with Gioacchino Antonelli, who is at NYU now, Enrico Pasqualetto, who is in Bascula, and Marco Pozzetta, who is in Naples. So the basic idea that we are going to discuss is that a lower bound on the Ricci curvature should imply a sharp concavity inequality on the isoperimetric profile. And the idea is that this should be true in great generality, but before getting into further details, I'm going to introduce the relevant background. So we are going to be dealing with the metric measure spaces. So let XDM be a metric measure space. And I assume that E containing X is a Borel set. Then in great generality, we can define the so-called perimeter of E with a variant of some of the constructions that have been discussed during the previous talks. So this is defined to be the infimum of the limit as I goes to infinity of the integral over X of lip Fi dm, where you take the infimum among all sequences Fi of Lipschitz functions that converge to the indicator function of your Borel set E in L1 block. Okay, and you would like these functions to be Lipschitz. Okay, and you define lip Fi, lip f of x for Lipschitz function to be equal to the lim sup as y goes to x of absolute value of f of x minus f of y divided by the distance between x and y. Okay, so there is a slight technicality in the case where x is an isolated point, but we will forget about it for the sake of this talk. Okay, so let me make discuss briefly a consistency check with the smooth case. So assume that XDM is actually the metric measure space coming from a weighted Riemannian manifold. Smooth complete Riemannian manifold. And let E be an open subset with the smooth boundary. Okay, then this is the right object to look at if we want to deal with the isoperimetric problem. So perimeter of E is equal to the weighted, if the manifold is weighted, surface area or surface volume measure of the boundary of E. Okay, so we have a notion of perimeter, which measures the surface area of a set in great generality. Then we can discuss the isoperimetric, introduce the definition of the isoperimetric profile in the following way. Okay, this is a function I, which goes from 0 to volume to the measure of x, which is possibly infinite, to the interval 0 plus infinity. Okay, and you pick any volume, and the value of the isoperimetric profile at that volume is defined to be equal to the infimum of the perimeter of E, and you take the infimum among all competitors which are subsets of X with volume equal to V, with reference measure equal to V. So you take A, E containing X, Borel, with the measure of E being equal to V. And this you can do for any value of the volume between 0 and the total mass of your space. Okay, so let's discuss 2 examples to get familiar with this notion. So example 1 is what happens in the case where the metric measure space is the Euclidean space with the standard structure. So let's say that x dm is equal to Rn with the Euclidean distance and the Lebesgue measure. Okay, then what happens is that I of V is equal to a dimensional constant, so a constant C of n only depending on the dimension, times the volume V raised to the power n minus 1 divided by n. Okay, so this is a consequence of the well-known sharp isoperimetric inequality on the Euclidean space. Okay, the second case I would like to discuss is the case of Rn, this time endowed with the Gaussian measure. So let's say that x dm is still equal to Rn with the Euclidean distance as a metric space. However, now I weight it with the Gaussian measure, so I put e to the minus modulus of x squared divided by 2 times the Lebesgue measure. Okay, and in this case, I won't give you the exact expression for the isoperimetric profile. However, I will point out that the isoperimetric profile solves a second-order differential inequality. Namely, what's true is that minus I second times I is equal to 1. Okay? Any questions so far? So broadly speaking, what I'll do for the rest of the talk is gonna try to convince you that it is reasonable to expect that there might be an implication between Ricci of x dm being greater or equal than k, and the isoperimetric profile of the metric measure space satisfying the inequality minus I second times I greater or equal than k. Okay, so this is a model case because as a metric measure space, Rn endowed with the Gaussian has a Ricci curvature bounded from below by 1. Okay, so the goal is going to be the following, and the plan is going to be that there are going to be 3 parts. In part 1, I'm going to try to illustrate where the inequality comes from. Okay, so this is going to be a part where I'm going to try to build some intuition based on the smooth case. In the second part, I'm going to briefly discuss what can be said for finite dimensional RCD spaces. Okay, and in part 3 is going to be dedicated to some speculations concerning what might be said if we drop either the finite dimension. So here I'm going to be focusing on the case where n is strictly smaller than infinity. Okay, and in the last part, the conjectures and open questions are going to be related to the case where you drop either the finite dimensionality assumption so this is very much in the spirit of the conference, or you drop the infinitesimal Hilbertian assumption. So you deal with finite dimensional, this time CDKN spaces. Okay, so let's start with part 1. Okay, let me call it the part about motivations. And let's say smooth background. Okay, so for this part, I'm going to assume that XDM is a smooth, complete Riemannian manifold. And though it's Riemannian volume measure. So I'm going to make the assumption that M is equal to the Riemannian volume. So it's equal to vol G, where G is the Riemannian metric. And I'm going to be assuming that the manifold is compact. Let's say that this is compact. Okay, so if you go back to the very definition of the isoperimetric profile, the isoperimetric profile is defined via a minimization process. Okay, and the first observation that we can make in this case is that actually that infimum under this assumption turns out to be a minimum. Okay, so in this case, by the so-called direct method of calculus of variations, for any V in 0 vol X, there exists a so-called isoperimetric set for that volume, where by isoperimetric, I mean that it is a minimizer for that minimization problem. Okay, there exists E containing X isoperimetric set with volume of E is equal to V. But as I said, isoperimetric means that it is an optimizer for the definition of phi. Okay, now a priori, so if you apply the direct method of the calculus of variation, you come up with a minimizer which might not be so regular. However, the so-called regularity theory in geometric measure theory tells you that this guy has actually almost a smooth boundary. Okay, so by regularity theory, partial of E is, let me be very sloppy and say that it is almost smooth. Okay, and for the sake of this talk, we can forget about the almost part and just assume that it is smooth. Okay, now the next thing I'm gonna do is to discuss two computations and illustrate how the Ricci curvature comes up in those computations. And then I'm gonna try to convince you that actually, if you combine those computations with the definition of the isoperimetric profile, you might be heading in the direction of such a second-order differential inequality. Okay, so let me draw a picture. Here is your manifold X. Okay, so you fix a volume. Let's say that it is roughly 1/2. You find a guy which minimizes the surface area among all subsets with volume 1/2. So this is going to be equal to E inside X. Okay, and then it is natural to look at the normal deformations of this guy. So I can introduce set E of t. So this is going to be equal to E of t. And E of t is basically obtained by pushing in one direction the set by an amount of t, where t is a positive number. Okay, so the precise definition is as follows. We let E of t be the set of those x in X, such that the distance between X and E, my original isoperimetric set, which was drawn here in the picture, okay, up to this boundary region. Okay, and I pick all the points whose distance from E is less or equal than t. Okay, and the first thing I would like to do is to compute the derivative with respect to the parameter t of the perimeter of this new guy. Okay, and what happens is that if I compute d over dt, let's say times t equal to 0 of the perimeter of Et, then a classical computation in Riemannian geometry tells you that this is going to be equal to integral over the boundary of E of h with respect to the surface area, okay, where h here is the so-called mean curvature of the boundary of E, which under these assumptions is a constant. Okay, so up to now, the Ricci curvature doesn't appear. The Ricci curvature comes up when you take the second derivative of this quantity. Okay, so let's compute. If you pick d over dt squared at t equal to 0 of the perimeter, the surface area of this guy, okay, then what you get is the integral over the boundary of E of the mean curvature square, and then you get two terms with the minus sign. The first term is minus the Hilbert-Schmidt norm of the second fundamental form of this hypersurface square minus Ricci nu, and this is integrated with respect to the surface area. Okay, and this is the second fundamental form. Okay, of the boundary of E, and this is the Ricci curvature in the unit normal direction, with respect to unit normal direction of the ambient manifold M with respect to a unit normal of partial of E. Okay, any questions? Okay, great. So now let's assume that our manifold has a Ricci greater or equal than kappa for some real kappa. Okay, so if Ricci of the ambient manifold is greater or equal than kappa, okay, then we can stare at this computation. Okay, this term we can keep. It is an innocent looking term. This term we can throw away because it's certainly negative. It's a norm square. And then we can estimate Ricci nu with kappa. Okay, and what you get is that the square over dt square of perimeter of Et is less or equal than integral over partial of E of h square minus kappa, okay, in the perimeter. Okay, now h, I told you before, is a constant, k is a constant, and therefore this is equal to h square minus kappa times the perimeter of E. Okay, and note that a priori you don't know much about h. However, the first computation tells you that h is related to the first derivative of this quantity. Okay, now it's not difficult to combine. So if we combine these two estimates with the following innocent-looking observation. The observation is that I of the volume of E is equal to the perimeter of E. Okay, the reason being that E was an optimizer for the definition of the isoperimetric profile. Okay, and on the other end, I of the volume of E of T is certainly less or equal than the perimeter of E of T. Okay, here the reason is that E is optimal. Okay, and the reason for the second inequality is that E of T is certainly a competitor for the definition of the isoperimetric profile with volume of E of T. Okay. So basically what happens is that the function which picks t and sends it to perimeter of E of t is everywhere above this function, I composed with the volume of E of t, and they touch at one point. We just computed the second derivative of this function, and we also know the first derivative. Okay, and if you combine all the ingredients, you can prove this second order differential inequality. Okay. Okay, let me briefly discuss references. So where does this argument come from? Okay, originally some of the ideas come from the original paper where Gromov proved the sharp isoperimetric inequality, the so-called Levy-Gromov inequality. Okay, and then the argument was refined by Bavard-Pansu in '86, and later by Gallot in '88, then rediscovered in a different context by Hubert in '03, and then pushed to a Niger level of generality by Bale in '03. And since then, it has been used by several authors at several levels of generality. Okay, any questions? Sure. Say it again. So your question is about the compact assumption? Okay. Okay, certainly an interesting question. I wouldn't. It feels so too strong to me, but I wouldn't know a counterexample. We can think about it. Thanks. Any other questions? Okay, so this was all I wanted to say about the smooth background and the motivation. So let's pass to the setting of RCD-KN spaces. Okay, so let's start with part 2. And as I anticipated, part 2 is going to be about what can be said for RCD-KN spaces under the assumption that n is smaller than infinity. Strictly, that n is fine. Okay, so the remark I would like to start with is that, okay, so the first part of the argument where you try to apply the direct method of the calculus of variation to come up with a minimizer for a problem, this is fine. This is not delicate in the setting. What becomes tricky is this first computation here. And the second computation where you take the second derivative, it's even harder. So the remark I would like to start with is that in this setting, so when the ambient space becomes non-smooth, then giving a meaning to the identity star and even harder than that, proving it becomes tricky. Okay, and a further comment I would like to make in that direction is that as of today, it is not clear whether the function that, it is not clear if the function which picks t and gives you back perimeter of E of t is differentiable at time t equal to 0. Okay, so, and in the joint work that I mentioned before with Antonelli, Pasqualetto, and Pozzetta, let me, sure. This we know. This follows from the theorem that I'm going to state in a minute. Okay, so it's going to follow, just to anticipate it, so the theorem that I'm going to state in a minute is going to imply that E of t has finite perimeter for everything. Okay? Thanks for the question. So in the joint work with Antonelli, Pasqualetto, Pozzetta, that appeared in 2022, okay, we get around this point by proving the following. Let me call it theorem 1. Okay, and the theorem has a spirit which is very similar to one of the arguments that were discussed in the previous talk. Okay, so assume that XDM is an RCD-KM metric measure space for K in R and N finite. Okay, and let E containing X be isoperimetric. Okay, which means that it minimizes the surface area, the perimeter that I defined before, among all other sets with the same reference measure inside the space. Okay, then the statement is that there exists a real constant C such that if you look at the distance from the boundary of this guy, and you look at its Laplacian, the Laplacian of the distance from this boundary is less or equal than a function which depends only on this constant C, the lower bound on the Ricci curvature, and the upper bound on the dimension, composed with the distance from the boundary of it. And this inequality is true on X. Okay, and so a few comments on the statement. So f of C K N is a comparison function. Okay, and the inequality is sharp in the sense that equality is obtained on model spaces. So this means that quality is obtained on model spaces. Okay, so two further remarks. Okay, so first, inequalities of this type were considered in the same setting earlier by Ketterer in 2020. So similar inequalities had been considered in Ketterer 2020. Okay, and second point that I would like to make is about the intuition. So why is such an inequality related to the computations that I did before in the smooth setting? Okay, and the intuition that was already mentioned in the previous talk is that if you have a smooth hypersurface in a smooth Riemannian manifold, and you compute the Laplacian of the distance function from the hypersurface, say that you pick the sine distance function, then along the upper surface, this is equal to the mean curvature of the upper surface. Okay, so in the smooth setting, Laplacian of the, say, sine distance function from partial of E is equal, if you restrict it to partial of E, is equal to the mean curvature of partial of E. Okay, for whatever set with smooth boundary. So this is meant to convince you that that inequality is really telling you something about the mean curvature of the set you're staring at. Okay, so a few comments about the proof. I'm going to be brief. The proof relies on a few ingredients, and I would like to point them out because they're going to come back when we discuss the extensions to infinite dimensional and nonlinear cases. Okay, so the first ingredient is a mild regularity result for isoperimetric sets. In RCD-KN spaces. Okay, so of course, in a non-smooth space, it doesn't make much sense to wonder whether there is a generalization of the classical regularity theory in the Euclidean setting. However, so Antonelli, Pasqualetto, Pozzetta in 21, and later Antonelli, Pasqualetto, Pozzetta, and Violo in 23. Okay, proved a mild regularity result for these guys. Okay, so I'm gonna come back to the details later if there is time. Okay, so this mild regularity result tells you that it makes sense to consider the distance function from the boundary. Okay, so the second ingredient is a series of different perspectives on the meaning of that Laplacian bound over there. Let me call it double star. Okay, so because I told you that the Laplacian inequality holds, however, I didn't tell you in which sense such an inequality is true. Okay, and those different perspectives so were studied in joint work with Mondino. And later we generalized them together with Gigli. And they further developed the original work of Gigli in 2015. After. Okay, and the last, but not least, key ingredient is a method for constructing, let's call them deformations on RCD spaces that we developed with Andrea. Okay, and further developing the joint work with Antonelli, Pasqualetto, and Pozzetta, which is inspired by earlier work due to Caffarelli and Cordoba. In the early 90s, and the work of Petrunin in 2003. Okay, so once you have such a theorem, okay, theorem 1 can be used to prove theorem 2. And theorem 2 tells you that, so on an RCD-KN space, so if you have a metric measure space which has Ricci greater or equal than kappa in the sense of RCD spaces, such an inequality is true. Okay. Let's say compact for the sake of simplicity. Okay, in the sense of distributions, it holds that minus I second times I is greater or equal than kappa. Okay, and actually, with the sharp Laplacian comparison estimate, you can prove a sharp form of this inequality where the dimension appears and the inequality is saturated on model spaces. Okay, any questions? Okay, so let me get into part 3. Okay, so which is about speculations. Okay, And as I mentioned, I would like to discuss the generalizations of these estimates in two directions, dropping finite dimensionality and dropping the linearity of the flow. So dropping the R assumption in the RCD condition. Okay, so infinite dimensional case. And nonlinear case. Okay, so let me this. So that one is the inequality that you get if you forget about the dimension. If you want to take into account the dimension, you get a better inequality that I'm gonna write in a second, where there is an extra term, okay, which is something like, I don't remember precisely, something like plus I prime squared divided by n minus 1. Okay, so when you send n to infinity, this is what you get. If you take into account the dimension, you get something stronger, and identity holds on the sphere, the hyperbolic space or on Rn. Okay. Please. This is so. This is a Riccati sub-equation. Let's say this is correct. Yeah. Okay. So in the direction of infinite dimensional spaces, let me raise a conjecture. The conjecture is that the inequality should be true, the differential inequality should be true also for RCDK infinity spaces. Okay, so if X D M is RCDK infinity, then minus I second times I should be greater or equal than kappa. And let me add the assumption that this is compact, or K is bigger than 0. Okay, to make it more slightly more less optimistic. Okay, in the direction of nonlinearity instead, this is I would like to call it an open question for reasons that I'm gonna discuss in a second. Okay, the open question is that if XDM is CDKN, maybe essentially non-branching. Okay, then the usual inequality should hold true. Okay, and the reason why I call it an open question rather than a conjecture is that, as far as I know, this is not known even in the case of smooth Finsler manifolds satisfying the curvature dimension condition. Okay, so this is an open problem. While so the smooth computations strongly suggest, I would say that this might be true in the RCDK infinity case. Okay, as far as I know, this has not been considered before even for smooth Finsler manifolds satisfying the curvature dimension condition. Okay, so let me proceed with a remark. Okay, so I don't want to be precise on this. However, the idea that I would like to convey is that at least morally, if you are able to prove such a sharp second-order differential inequality for the isoperimetric profile, then you should be certainly able to prove a sharp isoperimetric inequality. So at least morally, the sharp concavity inequality for I is stronger than a sharp isoperimetric inequality. For xdm. Okay, and so let's check that at least so that this the questions make sense in the sense that so in those cases a sharp isoperimetric inequality is already known. Okay, and indeed for RCD infinity cases with k bigger than 0. Okay, the sharp isoperimetric inequality is true and due to Mondino, Ambrosi Mondino. Okay, so the sharp isoperimetric inequality is due to Ambrosi Mondino in 2016. Where they further developed a semigroup approach originally due to Bacri and Ledoux. Okay, yeah. Semigroup. In 96. Okay, and the model for the sharp isoperimetric inequality for RCD infinity spaces is the Gaussian space. Okay, so Rn endowed with the Gaussian measure. And in the nonlinear case instead, so for essentially non-branching CDKN spaces, again, the sharp isoperimetric inequality is known to be true, and this is due to Cavalletti and Mondino. In 2017. How much time do I have left? Okay, I think it's a good time to stop here. Okay. Thank you for the attention.
Any questions?
I'm not sure. I wouldn't know how to. So you would be happy to know the answer. Me too. Sure. I see. I know. Yeah. Okay. So I can tell you the only reason why I put compactness here is because I discussed compact spaces throughout the talk. Okay, and compactness is very important if you usually compactness is important because it allows you to prove existence very easily. But you can get around that on locally compact spaces at the very least. So I put the assumption, the alternative assumption k greater than 0 here, because in that case, you have a log Sobolev inequality, and you can use that to prove existence of minimizers without compactness. Okay, and so if you drop those assumptions, then I wouldn't be sure that existence is true. However, it is not necessarily the case that existence is needed for proving such an inequality. Okay. I hope it answers the question. I never thought about that. It's an interesting question, but I never thought about it. For the equality case, So if k is positive, certainly yes. Okay. If k is equal to 0, I'm not completely sure. We can prove rigidity already. And if k is negative, I'm even less sure. The rigidity, you mean? I would expect, so I'm not completely sure. I think that there was work due to Gigli, Ketterer, Cuvada, and Ota, where they prove some rigidity statement for the spectral gap in the case of k positive, and the statement reads as if the spectral gap inequality is saturated for an LCD k infinity space with k positive, then it must split a Gaussian factor isometrically. Okay, however, so I never checked if a space, say that you have an LCD k infinity space, which is something times a line with the Gaussian. I never checked if this implies that the equality holds here. Okay, so if this is the case, then it's reasonable to bet that rigidity might hold true with the same statement. But otherwise, I wouldn't know. So if I understood your comment was that in the CD, say that XDM is a smooth Finite manifold with Ricci bounded from below by k and dimension n. Assume that all the isoperimetric regions are smooth, then you can do the same computations that we did, that I did in the first part, and prove this statement. I think that I get your point, and I agree. Okay, one point. So one reason why it might be reasonable to predict that theorem 1 extends to CDKN spaces. I don't think this is already known, even in the case of smooth Finite manifolds, where the isoperimetric set is not smooth. Okay, and the point that I would like to make is that I never use the smoothness of the isoperimetric set when I am on an LCD-KN space. So it's reasonable to expect that maybe the strategy might adapt to CDKN spaces. Even though there is a step of the proof where the linearity of the flow is used very heavily. So it seems technical because the statement should be true even for CDKN spaces, but the proof heavily relies on the linearity of that flow. Okay. So sure, thanks for the question. So in the non-compact case, so if you want to run the plan that I described, okay, the first, you stop at the very first step because the manifold is non-compact. You cannot apply the direct method of the calculus of variation. Okay, however, there are so-called generalized existence results for isoperimetric sets that had originally been introduced and studied in the smooth literature and have recently been extended to RCD spaces. And if you rely on those generalized existence results, then you can prove similar results if the ambient manifold is non-compact. On an RCD space, say, okay, so if the manifold is if the RCD space is compact, say that it is maybe something like a cone here, and then something like this here. Okay, so you have the Bishop-Gromov volume monotonicity, so you know that for any x in X, there exists the limit as R goes to 0 of measure of BRX divided by omega n R to the n. Okay, this follows by Bishop-Gromov. Okay, and the first statement is that the isoperimetric sets for small volumes are going to tend to go near to points where this limit is minimal. Okay, so in particular, say that your guy is smooth away from 2 cone points. Okay, so the isoperimetric sets for small volume are gonna try to converge near to this point. Okay, and then so if you don't rescale and you don't do everything, they converge to points. However, what's natural to do is to try to blow up the space. And if you rescale, okay, at least under some further regularity assumptions, say that XD, you look at XDHN, and you assume that this is RCDKN. Okay, then we can prove that the isoperimetric sets for small volumes converge to points of minimal density. And when you zoom up the space blows up to a cone, and the isoperimetric set is going to converge to a ball around the cone point. So it's very, very precise, the asymptotic for small volumes. What it looks like? Okay, so the boundary is going to, roughly speaking, look like a small ball near to a point of minimal density. The curvature of the boundary, so it's going to go to infinity. Would you like to get a better asymptotic? Okay, the better asymptotic is hard. So knowing how fast it converges to 0, to infinity, it should converge to infinity, but I guess, so I don't think that one can Taylor expand the mean curvature at a better order. Okay, this is related to the fact that the space is not so regular.